how many similar systems might already be hidden in existing meerkat survey data?
That's a very interesting question. And it actually speaks a little bit to how we found this one. So when we wrote the proposal to observe this pair of merging galaxies, it was not to detect OA. We were looking for we knew it was a strongly lensed system, and we knew it was gas rich, lots of molecular gas. So we argued that it was a good candidate to find neutral hydrogen gas, which is a really key important phase of gas in galaxies. That was our objective. We did find neutral hydrogen, but in absorption rather than emission. But then just playing around, we thought, well, hang on, the same data set contains the mega maser line. It's not far away in frequency space. We just checked, and then there was this huge, strong signal that we were talking about. It speaks to two things. Number one, these modern radio telescopes are so flexible and powerful that you can do multiple science cases in one particular experiment. Science cases that you weren't even planning to do because they cover such a wide range of frequency or a wide field of view in the sky. But the second thing is you really need the computational ability to process the data easily to find what may be hidden in the data already. So to your question, I would bet that there are a bunch of these hiding in existing data. It's just a question of, has someone gone to look at the right frequency at the right location and identified them? But I would definitely bet money that that's the case.
Yes, okay. And you mentioned terabytes of data and advanced pipelines. So I'm curious to know the biggest computational bottlenecks and whether machine learning techniques were involved in the detection.
Yeah, we didn't need any machine learning techniques for this. It was such a strong signal. It was just, traditional approach. You just saw it immediately. It was just there once you made the slices of images at the right frequency. But the biggest bottleneck is not necessarily the processing. It's the human in the loop. We basically maturing science data processing pipelines that take data from its raw format as the telescope writes out to disk to something that is science ready and that you see in this paper that is ready to be published, and we are confident that has been calibrated appropriately. But that those science data processing pipelines are not a click a switch and it's done. It's unfortunately every part of the sky is different, and every day a different part of the telescope might behave in a slightly different way that doesn't quite work out for the calibration pipeline. So it requires an expert astronomer to run the pipeline, look at the outputs, understand where things went wrong, understand what might be not quite right with the instrument or what might need to be tailored for that particular part of the sky that might have bright sources or extended sources, etc. And then you start again, but with that feedback loop in place.